Hello, everyone, and welcome to today's live broadcast, Precision Medicine 2.0, Impact Requires Data, Collaboration, Champions, presented by DavidShaywitz, MD, PhD. We're excited to bring you this educational web seminar presented by LabRoots. To learn more about LabRoots, please visit www.labroots.com. I'm Judy O'Rourke of LabRoots, and I'll be your moderator for today's event. This is an educational webinar and thus offers free continuing education credits. After the webinar is over, and to get your credits, click on the button located in the bottom left-hand corner of your web page. Before we begin, I would like to remind everyone this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. Just click on the green Q&A button located in the lower left of the presentation window. Type your question into the box that appears on the screen. We'll answer as many questions as we have time for at the end of the presentation. Also, please notice that you'll be viewing the presentation in the slide window. To enlarge the window, just click on the screen icon located in the lower right. Finally, if you have trouble seeing or hearing the presentation, click on the support button at the top right of the presentation window. Or you can use the Q&A button to let us know that you're having a problem. Thank you. Now I'd like to introduce DavidShaywitz, Dr. DavidShaywitz, the Chief Medical Officer for DNA Nexus. Dr. Shaywitz is responsible for driving clinical impact and shaping company vision, working closely with the DNA Nexus team of scientists and engineers and with external partners and collaborators. Most recently at Theravance Biopharma, he focused on strategy and business development and led a product team. Previously, he was a management consultant at the Boston Consulting Group, working with top 5 biopharma clients and co-developing BCG's internal view on personalized medicine. And before that, he was an early member of the Department of Experimental Medicine at Merck Research Labs. Dr. Shaywitz was also a founding advisor of Sage Bionetworks and a co-founder of the MGH MIT Center for Assessment Technology and Continuous Health. He graduated summa cum laude from Harvard, received his MD from the Harvard-MIT Division of Health Science and Technology at Harvard Medical School, and his PhD from the Department of Biology at MIT. Dr. Shaywitz trained in internal medicine and endocrinology at the Massachusetts General Hospital and conducted his postdoctoral research in Doug Melton's lab at the Harvard Stem Cell Institute. He currently serves as a visiting scholar, adjunct, in the Department of Biomedical Informatics at Harvard. Dr. Shaywitz writes regularly about medical innovation for Forbes and contributes commentaries to a range of leading publications. Please join me in welcoming Dr. Shaywitz. I will now turn the presentation over to him.
Great. All right. Fantastic. If I can get my slides up here now. Great. All right. Hopefully, y'all can see this. Greetings from scenic Mountain View. I want to start off on the first slide. So this talk is going to be about precision medicine and where we are, trying to take a realistic look at sort of what the journey has been to get here, and what are some of the real issues that we face going forward in effort to really, what is it going to take to achieve the impact that's bringing so many people together and is going to turn precision medicine from sort of an overutilized buzzword to something that can really inform and improve the lives of patients. I want to start off with a disclosure. In the disclosure section, I am an employee and an equity holder, shareholder of at DNA Nexus, a company in Silicon Valley, and then I have the adjunct role in the Department of Biomedical Informatics, as you can see. All right, so let me get over here. Great. So I wanted to start off with a little bit of the journey and how we got to be here. And I wanted to start off with sort of the era around when the first human genome project was being contemplated, to take us back to what some of the mindset and thinking was at this time. When as people started to contemplate, to get to think about the possibility of being able to start imagining sequencing a whole human genome, which seemed like a remarkable, almost unimaginable feat at the time. Folks were saying things like from Sidney Brenner, one of the real great geneticists in history. He said, with a complete DNA sequence and a big enough computer, you can, quote, compute the organism. less than a decade later, one of the fathers of sequencing, Wally Gilbert, said, with a complete human genome, quote, we'll know what it is to be human. There was such an outpouring of excitement, of sort of this sort of almost reductionist orgy of interest in all of this, that it led to some people to wonder, well, geez, are we really just overhyping what some of the promise is here? Has things gotten to be a little bit overheated? And in fact, there was a really powerful commentary that Harvard geneticist Richard Lewontin wrote for the New York Review of Books in 1992 called I Dream of Genome, where he essentially suggested that our view of the human genome, and this was his quote from the article, essentially reminded him of a fetish, which he defined as, from the Oxford English Dictionary, of course, an inanimate object worshipped by savages on account of its supposed inherent magical powers or as being animated by a spirit. And his point, obviously, was people were imbuing so much power into sort of the DNA itself and thinking that it was going to be sort of the magical answer for everything that ailed them and ailed humanity. And in fact, it's not just DNA for which this is true. When we think about other more contemporary examples, I mean, this is just a representative sampling, but essentially it could be almost anything that you might put at the middle of like a buzzword bingo, a scorecard if you had the opportunity to select the space. Something, we think about it maybe in terms of DNA, the Genome Project, but we've also heard it for design's the answer, or now big data or mobile. And there are these buzzwords that tend to sort of have, on the one hand, really be powerful, but that we tend to bring this sort of extra degree of power and belief, and this real belief in. And one of the problems of this sort of, these extravagant expectations is that then there's a predictable reaction. So after there was so much excitement from some quarters about what was going to be the promise, which some thought were going to be maybe the results were going to be seen more immediately, there was then this reaction where there was this, I call it reaction 1.0, which was this sort of this disappointment. We fought cancer, and cancer won. Sharon Begley, always and still is at the top of the game in medical reporting, wrote for Newsweek at the time. Gina Colada wrote for the New York Times, Advance is Elusive in the Drive to Cure Cancer, another terrific article and series. So there was a real both hope and then sort of almost the predictable sort of trough of despair, as it turned out that even once you were able to sequence the genome, things were still really hard. So, which brings us to Genomics 2.0, which is essentially introduces at least two new phenomena. The first is the idea of next generation sequencing, the ability, frankly, largely based on sequencing instruments from Illumina, but also from other folks, in which the cost of sequencing a genome has gone down multiple fold. I mean, an unbelievable number. They say it's sort of happening faster than sort of Moore's law is sort of the expression. The left figure here would be the middle of any sort of genomics buzzword bingo, the figure that's in every paper and every talk. But the idea is that the cost is going down and the data volume is going up. And in fact, there's a really interesting paper by a group from Illinois and from Cold Spring Harbor came out last year that actually talked about the amount of data that's being produced and said it may even be more than the amount of data that's associated with Twitter, with YouTube, with astronomy. They said that we should have a new term called genomical, which is sort of even more than astronomical, to kind of describe the massive volumes of data that are produced and are likely to be produced from next generation sequencing and the next generation sequence type of analysis of data. So what do you do about it? Well, we can look to Craig Venter, one of the obviously pioneers, along with Eric Lander, of the original human genome effort. There's a public and a private effort, and obviously Venter looked at private effort. He's now very involved in several other companies. And he testified before Congress in 2014 and said that the real key is, yes, NGS, but it's also the cloud and the ability of the cloud to manage huge data volumes. He said the most important change in the landscape that he defined are in the computer world. And he said, quote, the use of the cloud is the entire future of this field. Obviously we should have perspective. If the Human Genome Project was the expression of Genomics 1.0, Genomics 2.0 perhaps is the expression of it is this precision medicine initiative, which was privileged to be at the White House in the East Room in 2014 in January when Obama announced it. And it was really exciting. The concept of precision medicine sort of evolved after personalized medicine. There was an IOM report written by Susan Desmond-Hellmann and others that really sort of focused on trying to really utilize more precise measures of analysis and individualization to identify and deliver improved treatments. And the other thing that's incredibly important about the Precision Medicine Initiative is that it really views the patient as a partner. It tries to evolve from kind of a paternalistic history of where research is being done to the patient who is viewed as a source of data, and instead to have recognize that the patient is a vital partner, in many cases even the driver of the science that's being done. And the idea is to have much more of an equal, shared, collaborative relationship. And this is an incredibly wise approach, and it's also driven by some of the technology and some of the advances in science and in thinking about how you approach an initiative like this. I'm particularly excited by some of the approaches which we'll talk about that are developed by Sage Bionetworks and folks like John Wilbanks in terms of how you really apply consent in a useful and appropriate fashion. Now, once the Human Genome Project was announced, once the Precision Medicine, the PMI initiative was announced in 2014, and there was a lot of excitement everywhere you turned. It was precision medicine, precision medicine, precision medicine, and it got very, very buzzy, leading many people, many very, very smart people, to express concern. My friend Michael Joyner from the Mayo wrote a very influential op-ed in the New York Times saying that, oh, moonshot medicine will let us down. Michael Millinson, a fellow contributor at Forbes and a number of other roles, wrote a thoughtful piece about the kind of overly aggressive use of precision medicine branding in some diagnostic tests. And there were kind of a number of other articles as well. Thoughtful, appropriate articles that attempted to contextualize the excitement around precision medicine and to say we need to draw distinctions between the promise, which is why so many of us are excited about this, but to make sure that we do this in a very grounded way. We understand where we actually are, where we're starting from, and not essentially offer false hope and that will only lead to sort of further disappointment. So the way I would characterize this is to say what we really need in this field is tangible impact. So I'm using the example, of course, of Uber, not crystal clear, not that we need the Uber of anything. We're not looking, no one is trying to, this talk isn't about trying to be the Uber of healthcare, the Uber of genomics, the Uber of Uber. What we're trying to do is to say, one of the things that's so compelling about Uber is, really compelling about it is that you use it once and you immediately get it. I mean, maybe you try it out because, you think it's trendy, you think it's kind of cool, it seems like a neat concept, but you use it once and it's like, oh, this is really convenient. This is how I can get from place A to place B in an inexpensive, convenient way. And it's intuitively obvious, and then once you have the ability to use it, you start to get grumpy when you land in some city and you can't, they don't offer Uber, or it's not at the airport or something like that. It becomes so obvious how it's useful, and then you start to expect it and then get disappointed when it isn't available. So I would say it's that level of immediate utility, of tangible impact, that precision medicine is aspiring towards. And when you get to the point where you could, in the same way that you sort of would just instinctively, many of us, reach for Uber when you want to go from place A to place B, similarly, you would want to reach, you'd demand that particular genetic capabilities and tests are present when it has that degree of immediate overt utility. So what I wanted to next do is to go through and to present what I would describe as green shoots, some of the early signs of progress, some of the signs that I think reasons to be happy, to be hopeful that progress is being made, that we are moving in the right direction. To be clear, we're not at the Uber level of obvious tangible impact for many applications of genetics, but we're getting closer in some. So one area is the area of family planning, and two areas around this. One, there's a lot of use today in the area of carrier screening. Couples who are married or thinking about having a kid will very often have carrier screening to assess the potential risk that a potential future child may be subject to. And in this presents an example, courtesy of counsel. Other companies are doing similar things like Natera, of carrier screening, where you're looking at, where in this case, a couple were tested. They were found to both be carriers of essentially a recessive gene that, if present in both copies, could be devastating. And they actually elected to have a procedure called pre-implantation genetic diagnostics, where you're able to evaluate at a crazy early stage cells and determine and essentially implant just the ones that are don't carry a homozygous mutation. And when they did that, they gave birth to a healthy baby girl. Now, most folks are not getting PGD now, but it's just an example of a discrete application of this technology. Another example of just how fast things are moving in this space is the non-invasive prenatal testing. So this is when not everyone undergoes this, but many pregnant women, and couples do undergo this. They sort of have a screen at around 10 to 12-ish, I think, weeks for 14 weeks maybe of pregnancy, looking for sort of chromosomal abnormalities. And typically there's first some screening tests, often involving an ultrasound and some blood tests. And then historically, based on that, one would then, if the screening was potentially worrisome, the next option is to have what's called either an amniocentesis or a choriocentesis that actually directly samples blood, blood or samples cells in amniotic fluid and evaluates it, essentially trying to get a sense of whether there are particular chromosomal abnormalities in the early fetus. Now, because of the new emerging technologies, non-invasive prenatal testing, for example, offered by Natera and others, one is able to have a blood test, just a peripheral blood test done at the early stage of pregnancy. And if it's negative, the negative is it's not definitive, but it's essentially better than the other type of testing that it obviates the need in some cases to have an amniocentesis or a choriocentesis. And because, therefore, reducing the risk of an accidental, reducing the risk of injury to the fetus and to the mother, and frankly, saving money for the payers, which is why some payers now are actually paying for this advanced genetic testing that really went from initial concept developed by the lab at Stanford to a implemented test in a remarkably short amount of time. So another area which we hear so much about is oncology. The idea of that cancer, as you read, is a molecular disease. It's defined by a range of specific mutations, and there are an increasing number of medicines that target specific mutations. And sometimes, for some types of cancer, you sort of have a sense of what some of the mutations might be, and you look for it, and you can pick your medicine based on that in some cases. Then in other cases, one of the things that Foundation Medicine, for example, another company has done, is really been able to sort of find, and for some patients with some types of cancer, been able to identify by using genetic testing mutations that one might not have thought a particular cancer, or might not have immediately thought a particular cancer might have, and by identifying that mutation, suggesting, not in most, but in some cases, a potentially novel form of therapy, a drug that might be usually thought of in cancer A, but it apply this in cancer B, and you're able to do it because you've identified a particular genetic mutation and give the appropriate therapeutic. This is another example in Mendelian disease, such as cystic fibrosis. This is an incredibly inspiring example. This was this story I heard again at that Precision Medicine initial event in 2014. Bill Elder was at the time a med student. I think he's an intern, a resident now. He is somebody who suffered from cystic fibrosis, and he said but he had a very specific, not the most common form of mutation for cystic fibrosis. It's a different kind of mutation, very rare. That's only present around 4% of the patients who have cystic fibrosis. But it's a type of mutation for which there is a target therapy developed by a company called Vertex that is specifically beneficial and approved by the FDA for patients with this particular mutation. He's appeared to respond incredibly well, was actually Michelle Obama's guest at the last year's State of the Union, and when Obama was talking about him this year, at the Precision Medicine event, apparently he said that he never expected, now he's contemplating being a dad and a grandfather. He said things that he never would have contemplated when he was growing up with cystic fibrosis. But this drug has not only helped with his, help with his breathing, help with his quality of life, but also his trajectory, and has really brought incredible new hope to him as a result of this targeted treatment. Here's another example in the area of infectious disease. And this is a story that, including the patient's name, that was written about extensively in the New York Times and other places. This is a boy who has a severe immunodeficiency disorder, who presented with an acute illness of unknown cause. And essentially, no one knew what was going on. He wound up essentially a pundit in the medically induced coma, as the staff in the hospital frantically tried to figure out what's going on with him. No one knew what it was. They went through the usual differential, and they didn't really come up with anything that seemed effective. Kind of grasping for straws, they did this approach developed by Charles Chu, where he samples a range of fluids and essentially has a protocol where he looks for evidence of known infectious agents. And in this case, we're able to identify a specific bug for which there's there's an excellent treatment. In this case, it's high-dose penicillin. The boy was treated with the medicine and was cured back to baseline. So went from being a pundit medically induced coma that had everyone baffled and struggling with what to do, to a specific diagnosis, a specific treatment, and 100% different trajectory in his life. And in fact, we're again, Nexus and others are privileged to be partnering with the investigator Charles Chu at UCSF, who led this effort in a pilot project funded by the California Precision Medicine Initiative, trying to take the methodology used for this and really blow it out at scale. And then the DNX is working through the cloud aspect of it, so that really the analysis, the sequencing can be done in any of the large number of places, and then analyzed centrally. And again, this is really the brainchild of Charles Chu, an infectious disease doctor at UCSF. All right, so another example, and this is really one of my favorites. I find it just incredibly inspiring. How do you use what you might call the new genetics in drug development? And sort of the poster child here is a target called PCSK9. And it's a broader, sort of the story here is, there was a lot of research, but the kind of canonical example, or the patient who sort of represents the story best, is a woman who, in this Nature Review article, a Nature article by Stephen Hall, his name Charlene, was called out as named Charlene Tracy from Texas, in the Dallas Heart Study, I believe. And she was somebody who essentially is a healthy mother of two, but who has crazy, crazy low LDL. But otherwise, I mean, but nothing else worrisome, nothing else, just this really great level of like bad cholesterol effectively, but everything else is fine. And it turned out that she has kind of loss of function mutations, a mutation in both copies of her PCSK9 gene. So the idea is this is then suggests, and this is not just from this research, but as an example of it, of multiple convergent lines of a lot of different types of research from basic to translational that demonstrates if you can, even though this mutation is incredibly rare, by the absence of PCSK9 can be associated with really low LDL, essentially a great cholesterol profile, and without doing any other harm to the person. In other words, the person was able to do fine without any PCSK or any meaningful level. I don't think there's any level of PCSK9 around, i.e. suggesting PCSK9 might represent a very good drug target. There's now been an explosion of interest in work that tries to look at just these type of things, that tries to find these sort of rare loss of function mutants. There's been some wonderful work by Dan MacArthur DeGroat on this, and many others that are really trying to say, can you try to identify these sort of rare loss of function mutations and gain insight into biological processes. And in fact, the sort of one of the best examples, and again, we're at DNA Nexus, we're privileged to be involved in this, really privileged to be involved in this because it's just this beautiful, very, very well thought out effort that represents collaboration between the incredible Geisinger health system, when the project was launched, led by Steele, and really the genetic part led by David Ledbetter, this remarkable visionary guy. And on the Regeneron side, George Yankopoulos, who's really driving a research-driven, research-based biopharma company that, led by a vision that he's had. And it's just exciting to see this play out. Where what they're basically doing is they are sequencing, a whole exome sequencing, it's called, a huge number of fully consented patients in the Geisinger population. The samples, the identified samples are sent to Regeneron, where the sequencing is done. All the data are shared from clinical and genetic data are shared and analyzed on our cloud, and that's sort of integrated and interrogated. But the idea is that these data are being used to both drive drug discovery and the sort of trying to find the next PCSK9 type of thing, and also used to provide clinical input to patients, and also driving clinical research of the type that Marilyn Ritchie of Geisinger, Penn State and Geisinger, but I think it's primarily at Geisinger now, are at the absolute forefront of. And in fact, just as an example of this, the Regeneron-Geisinger collaboration resulting in work that anybody can, in accessible work that anyone can read. This was a paper, a target identification paper, a particular variant associated with risk for coronary artery disease that came out early March in the New England Journal, where essentially they were able to do their own version of something like the Dallas heart failure, not quite, but it was essentially, they had a question about whether a particular gene might be doing something, might be involved in coronary artery disease. So they were able to screen their database for variants that might be loss of function in this particular gene. They were able to analyze a range of clinical endpoints or clinical parameters, which they've also categorized and curated elegantly. And then by integrating the data, setting it up appropriately, setting up the appropriate controls, and essentially running what's typically a multi-year study at the push of a button. I mean, it was more complicated than that, but that's the basic conceit. They're really able to drive some very interesting work, which then they were able to further validate using additional in-house technology, antibody development technology that Regeneron has. Okay, another example of the power of genetics is, and this is a really, both the power and, as we're going to come to, as much the limitation of genetics too. This is an example you might have read about a couple of years ago in the New Yorker, in an article called One of a Kind, about a boy who was born with a condition of unknown cause, and ultimately genetic testing done at the time at Duke identify, and at I think the ultimate testing was actually done at Baylor, identified a particular mutation that was likely causative. So it turned out that using clinical exome sequencing, such as done at Baylor and at other places, was able to relatively easily, not totally, relatively easily identify the causative gene, but then identifying a patient community and learning about it was far more difficult. And we're going to come back to this important, really social challenge in a little bit. So halfway mark, maybe I wanted to spend some time talking about, okay, that's sort of where we are. Two ways one might contemplate what is to be done. So I'm calling this lens one, looking at sort of this framework, and I want to sort of work through it, talking about push and pull, pushing in data and pulling out applications, or the role of meaningful applications to really sort of pull the system forward, and then obviously the pivotal role of both basic science and translation. So in driving the system forward, there's an urgent need for really more data. Things that are going to generate more data include cheaper testing, as you're going to sequence more patients if it costs $1,000 and if it costs $1 million, and if it were to cost $100, you'd even sequence more. So I think as the costs continue to drive to come down, to be driven down, there's really going to be a lot more sequencing. Though it's important to recognize that there are the costs of the sequencing itself, but then there are also the costs of the interpretation, though that's coming down as well. Then the other aspect of more data is really empowering patients. And it's historically challenging to wrest data from most healthcare organizations. Biden was talking at Health Data Palooza just this past week about how unbelievably difficult it was for him to extract his son, obviously tragically died of cancer and was being treated at both a Naval Hospital and at MD Anderson. And to get data to move from one hospital to another, even though his son-in-law, he said, was like a leading surgeon, and even though he is vice president of the United States, he was really just beyond how difficult it was to actually get the data. And even getting the data, it's like getting it on a disk, sort of like circa 1980 to actually do. So this is, the technology is better than this in every other area, and it really needs to change. And the idea is that to the extent organizations may resist releasing data, although that's really changing with some policy, the idea is that really data doesn't belong to organizations as much as to the patients. And to the extent that one can really prioritize and empower the patient as the center of this, this is the point of Eric Topol's book, The Patient Will See You Now. It's the point of the Precision Medicine Initiative, where the goal is to empower the patients. It's the point of the Get My Health data movement. It's the point of the Pasteur program that we started 16 years ago with the idea of our patients as partners in discovery with Denny Osceola at Mass General. It's really the focus of it is really recognizing that the locus of ownership, power, and control really belongs with the patient. And to the extent that the system doesn't always operate around that, but really they pay lip service to it, but to the extent that that really is true, it would be better for data movement and insight generation. Next, more pull. And this means that the results that you get from genetic tests have to really be as useful and as reliable as possible. And there are a lot of aspects to this. I like the ACCE framework, which developed by the CDC. You can find on their website many nice posts by Moon Kudri there. Really a terrific thinker in terms of genetics and public health at the CDC. And this is a very helpful framework where you sort of say, well, sort of the innermost layer. First, you have to make sure the A is for analytic validity, to make sure that you say that if your test says there's a T at position 24, it better be a T at position 24. But to make sure that you're calling it right. And this is a lot of the effort of the Precision FDA initiative, which I'm going to get to in a minute, again, which we're privileged to host or to build or to support it. Then the clinical validity, which means that, okay, let's say that there is a T there. You say a T impacts the metabolism of your drug or is associated with a particular disease. Well, does it? Are you sure you're right about that? And this is especially interesting in the context of some recent work, very exciting at the East London study, I believe, from Dan MacArthur, name comes up a lot, doing just so much amazing stuff. This is an example of work where they sort of look at a population of folks looking essentially for these sort of loss of function mutations. And what they found to their surprise was there were a number of mutations where the literature had said, oh, if you have a particular mutation in this gene, you have it's associated with a very, very bad consequence. For example, you have for sure going to have hearing loss. Mutations in this gene so if you don't have this particular gene and it doesn't code a protein right, you're going to have hearing loss, or you're going to have this problem, or you're going to have that problem. And then they found all these examples in this population where that didn't happen. It turns out that while the initial folks who were studied, maybe they were all in one particular population where that mutation was associated with hearing loss. Turns out in another population, well, it wasn't. In fact, the people seem to hear just fine. So it's really important that one sort of gets this right, and that in particular you can imagine, and again, Heidi Riemann talked about this in a really nice Ed Young Atlantic article, in a really poignant story about how, telling someone that a particular mutation that was identified, I think in prenatal testing was, she goes, oh, the data suggests it's harmful, the couple ultimately terminated the pregnancy, and then she comes back, kind of running back after the fact in a couple of weeks, saying, oh, there was some new data. It turns out it's not a bad mutation. It may be fine, but it was sort of too late. So that's sort of a pretty sobering, and again, I'd look up that Ed Young story in the Atlantic. It's another typically great Ed Young article. And then finally, there's the improvements in clinical utility. And let's say you accurately say you have mutation here, and this is associated with metabolism of warfarin. Boom, we know that. So what? You still pay for the test? Does it still make a difference? Can you do anything with the result? And there's a healthy debate here about what does the word actionable mean. In some cases, you can say all knowledge is actionable. It's informative. It's good to know. Knowledge is good to know. And then from the perspective of a payer, they're like, for example, the specific question in the case of warfarin, you have a blood thinner with rat poison. Do you use warfarin? Should you test warfarin? If you're going to start someone, if you're going to anticoagulate someone, is it better to start them on? Do you just pick a random dose, or do you try to have it pick your initial dose informed by their metabolism? And you think, well, my goodness, if there's a big genetic component, which there is, unarguably, clinical validity is there. You should test it. But when they've done randomized controlled studies of this, it's really hard to find any meaningful impact of doing it. Of actually doing the genetic test, because clinically, one, the genetics only counts for sort of half the variability, and there's a whole other component where, in any case, you're going to want to go low and go slow, which is how you start people on warfarin, and you're going to want to do that in many cases. So even though there is just genetics, and they're always reading all these statistics, people are always quoting about how many drugs have a genetic component. The real question is, how does that knowledge meaningfully impact what you're going to do clinically? And there are some real instances where it should. I mean, there's a drug, irinotecan, where it has a genetically related impact, sort of GI impact that's completely dependent on whether you have one form of gene or another. And now it's more like if someone has that side effect, like, oh, maybe we shouldn't give you the drug. But obviously, if someone shows up with the phenotype, with the genetics in hand, it becomes immediately unethical to give them a drug that they're going to respond poorly to. And there are other examples of that as well. This is just reminding here of the pivotal, critical, underlying role of basic science, of curiosity-inspired research. Obviously, one of the best examples we're seeing of this is CRISPR. CRISPR is sort of this pioneering technology, this gene editing technology. And it was discovered from basic science. People were exploring how bacteria protect themselves from viruses. And in the course of it, they discovered this enzyme that turns out to have additional uses. And so it's obviously the NIH has played a pivotal role in driving this. And there's also an essential to increase the rate of knowledge turns, as we're going to come to in a minute. And then there's the issue of more translation. And this has been sort of something I've been really focused on, I think, my whole life, this often underappreciated challenge. And it's this: science doesn't generally find its way into practice without deliberate effort. It's sort of like the underpants gnome problem of South Park. Step 1, make a lab discovery. Step 2, step 3, clinical impact. And there's this kind of step 2 in there that often gets underappreciated. And so there's a really important role for how does that translation happen and how can it be accelerated. Non-trivial is somewhat of an understatement. And I think that the 3 elements that I would really call out as being critically important, and I've certainly tried to focus, are there's a vital role in driving translation of engaged patient participants, patients who are driving, who are urging the science, who are saying we need, who are very engaged in everything. We really need to pull this forward to make sure the science doesn't just stay in the lab, and really sort of is driven by the clinical urgency. Next is the role of frontline providers, the physicians and caretakers who are seeing what the actual clinical needs are, who are recognizing the limitations of and the capabilities of existing treatments, and who often have the most astute insights into sort of what might be needed, what are some of the issues, and can really play a particular role in driving science forward. And I look to really role models here like Einar Sawyer of UCSF, who I think has written and described more elegantly than anyone I know the power and importance of frontline providers. And then finally, and I know I sort of kind of harp on this at length, but I really see sort of healthcare entrepreneurship as the rawest experience of translation. I think this is fundamentally what healthcare entrepreneurs do, is driving the promise of science into something that's actually robust enough to give to patients and to be able to do. Not the only ones by any means, and really you need everybody. But I think in terms of the conversations I've had and the folks who are most intent, who are, let's say, just intensely focused on this very specific problem of how do you get something that seems promising, but often is a little bit fragile, how do you drive that to actual application? And I think this is why there's such an important role for entrepreneurs in healthcare and the life sciences. So I wanted to take just a minute or two to look at this through what one might call lens 2. A little of the consulting background there, everything has to have a lens. And this is sort of the idea of data sharing that's really been in the news lately with the concept of data parasites, data sharing, data silos, all of these things. It's really clear that everybody's really focused on it. Obama talked, again, incredibly articulately about the challenges. Biden talked very poignantly about it. Huge efforts from Republican leadership in the Senate and in the House to really bipartisan efforts in Congress, to be fair, driving the focus on data sharing and interoperability. Everyone recognizes that this is a good and that this is important to accelerate. Though how to do it is the old belling the cat problem. So data sharing, and again, most talks after, the same way most genetics talk have the cost of sequencing going down, most data sharing talks either use the Tower of Babel metaphor on the left or the data silo metaphor on the right. And it's sort of unfortunate that these are the two choices. What I wanted to produce, just as an example, this is course, and don't send me emails that the math isn't actually how it works, I know that. But at a very, directionally correct maybe level, just sort of highlighting the value of networks versus sort of silos. And the idea is that the value of a network is proportional to the square of the nodes. So, and again, this is arithmetic my children can do, but the idea is that as you go, as you have more and more nodes, the data loss that you have, the difference between here and here is essentially the cost of not sharing, and that's what's so profound. So some of the real inspiration for this I take from Josh Sommer, who I was privileged enough to listen to at the first Sage Bio Network. Sage Bio Networks, I was privileged again to be a founding advisor of it, run by was founded by Stephen Friend and Eric Schatt, and really focuses on data sharing and approaches for rich and inspired data sharing and open science. At the first conference that they had, an incredible speaker, Josh Sommer, who was, when an undergraduate at Duke, he was diagnosed with a rare cancer called chordoma. And then he sort of recovered, fortunately, with a lot of support from his mom, who's a physician there, I believe. And then, to the point where in 2014, he's, now Forbes 30 under 30 leader, very, very well earned, much deserved. But he really talked about the urgent need to share data and how unbelievably frustrated he was trying to get academics working on chordoma to share data with each other. So Biden wouldn't be surprised, but a lot of people may have been. This is, the late Andrew Grove is also incredibly inspiring. And he wrote about this in JAMA in 2005. And he, I had several discussions with him, and he really sort of highlighted this point that he was trying to figure out how come industries like technology, like microchips, seem to, just, generate so much progress so fast, and why isn't it true in healthcare? Obviously, it's complex. There are multiple differences, but he thought that it could really boil down to the disparate rate of knowledge turns between the two industries. And he said knowledge turns, which he defines as the indicator of the time it takes to go from the hypothesis to result, and then you develop a new hypothesis. And basically, it just takes so long because of the degree of data of data hoarding. And just the reluctance of, and he was referring to academic investigators, and I'm sure it's true across the board, to richly share data with each other, even though human lives are at stake. And in fact, to come back to the case again of Matt Might, who, not the guy in the picture, but maybe the inspiration, who in order to, so once he had the identification of the mutation for that his child, the NGLY1 mutation, when he wanted to try to find other patients, the science community wasn't as helpful as the really true dense networks that you had from more traditional social communities like Google and Reddit. And basically from writing a blog in a way to sort of set up to generate a lot of hits that was rerun on Reddit and other social media sites, that's actually what in his case generated the leads that was able to help him find other families. There's a kind of a robust, I want to make sure I get to everything, there's a robust debate now about whether the problem with data sharing is that essentially it's not in the economic self-interest of folks to share data, as some have argued, or if it's just they don't really have the capabilities or experiences or the governance to be able to do that. And there's an interesting perspective on that. It may have elements of both. My 2 cents on this is that I think medicine, on the one hand, is intrinsically conservative, small c, cautious and slow to change. But I think there's an incredibly deep-seated commitment to doing right by patients. And the way I mean, as you can sort of gather, a theme of this talk is that I think, people are convinced by proof, but that as the benefits of sharing and the harms of siloing become increasingly concrete, become palpable, come to the point where it's so overtly, like the same way like denying someone like a vaccine would be unethical. You don't give them a vaccine, or someone has strep, you don't give them penicillin. That's unethical. You wouldn't think of doing that. Similarly, if and when we get to the point, I imagine when, where, the idea is once it becomes so clear that everyone benefits from this robust sharing, I think we'll get to the point where it gets to the point where it becomes unimaginable not to do it, again, provided it can be done in an appropriately consented, safe, and secure fashion, which is sort of an important qualifier, obviously. I think I may have a perspective on this that may be informed by, again, at DNA Nexus, we've really had a privilege of being the platform that's helped bring so many different teams, so many different investigators and data and science together, that we've really seen the incredible, and personally I've seen just the power of collaboration and of robust data sharing, and what happens when you bring the researchers and data and the tools all together in a common place, in this case on the cloud. So there's a number of these consortiums, ENCODE and CHART, NIH sponsored, the Regeneron Geisinger example I just discussed, and then Precision FDA. And I'm just going to give a minute or two on a couple of these. The ENCODE consortium is a consortium that's designed to essentially develop and to sort of characterize a parts list of what are the sort of functional units of functional parts of DNA. Sort of regulatory elements and a range of other elements are sort of a part of the genome. And there are a range of investigators, mostly in the US. And the key design features of this, which I think relate to the fact that it's been so effective, is that there's a central port in this case, and this isn't the only way to do it. In fact, we've worked with a number of different approaches. So it's trying to share examples of things that have worked. One is the idea of a central portal where all sort of the data is received. And the data are subject to very, that essentially, in order to be my understanding of this, is that for the investigators who are involved, who are contributing to the project to be essentially fully reimbursed by the government on their grants, they actually have to submit, the data they submit has to pass a predefined quality control, and also has to utilize very specific vocabularies and ontologies so that everything can be classified in a standardized fashion. And I think that's been critical to the success. And equally critical, maybe even more so, is the role of data provenance and process transparency. Even if people say they're doing the similar things, you have to actually know how data were analyzed and be able to track the provenance of each piece of data and have very defined pipelines. So this shows a kind of metadata that's collected and associated with each of the bits of sample in ENCODE. And then this sort of highlights the importance, again, these slides are all courtesy of the PI of the ENCODE Data Coordinating Center, Mike Cherry of Stanford, amazing investigator, is the role of not having a black box pipeline, but on the other hand, being able to understand exactly what's involved and being able to track each of the individual steps and be able to say, this piece of data came from here, came from here, came from here, and be able to track it in an incredibly granular and essentially in an immutable fashion, which is, of course, exactly what our platform enables. The other example I want to get to is Precision FDA, which is a community platform for NGS assay evaluation, developed really the brainchild of one of the most brilliant people I've been privileged to encounter in government, Dr. Taha Kashoot. Just essentially just this like unbelievable visionary person who started off at the CDC, did a bunch of amazing stuff there, then came to FDA where he sort of developed the concept of open FDA. He sort of a total, what Stephen Colbert might call an it getter, just understands data, understands sort of how it moves, how it's structured, what are the challenges, and is also able to get stuff done in just an incredibly inspired way. Anyway, he had this idea of building this community platform. We were privileged to be selected to build it in conjunction with them. We were able to actually build it from the initial code was written in something like the beginning of September, and we were in beta for the community by in something like 3 months. It's an unbelievable accomplishment. It shows how agile development can work. This is sort of the splash page, demonstrates some of the range of capabilities available on Precision FDA, where you can sort of upload files, you can run comparisons. This is sort of what the ecosystem looks like, where people come, each organization can have, it has access to a private area, a data sharing area. Note that the FDA is not in anyone's private area. They were, interestingly, during the design process, even more insistent on that than you might have, there are a lot of people externally are like, oh, the FDA wants to pry my private data. It turned out that's the last thing they wanted to do, and they wanted to not have anything to do with anyone's private data, but just data that was explicitly shared in the community here. This demonstrates the rapid and global growth of the community that now has, and again, thanks to FDA for this slide, over 500 organizations and over 1,000 members. This is an example of the range of apps that are on the application. I can see I'm getting low on time. The types of comparisons you can run against provisional or benchmarks. And then what they've also done is set up these community challenges. They're actually already on the second one. There's consistency challenge, and the truth challenge has now been launched, where really the community essentially competes and submits results before the results are known in some cases, in the case of the second challenge, and tries to see how well their approach is. And again, this is not for regulatory purposes, it's for sort of process development at the moment. And this just sort of demonstrates the value of a community. So this is sort of a discussion area and sort of data and sort of the submission area within one of these challenges. And you can just see the incredible broad community participation from folks at the Broad, from companies, Sanofi, Roche, Garvin in Australia, UC Santa Cruz. I mean, just and many others. So there's an incredible broad range of interest in, essentially, this is an example of when you build it, and if you do it nicely, people will come and people are engaged. So a couple of, maybe in the last 5 minutes here, a couple of kind of final words. My own thoughts on all the data sharing stuff is, I think it's really good to have a problem and use case in mind to understand what you're solving for versus sort of boiling the ocean. I think Regeneron is really one of the best examples of this that I've seen. They really had this incredible vision. And again, it's been an incredible privilege here to work with. The people we tend to sort of work with are the people who have the vision, the sort of are a couple of years ahead and say, aren't worried about, well, let someone else do it first, and if it's okay, we'll kind of, crawl in after them. These are people who have a vision, like George Yankopoulos. The man has a vision. This is how we really can see drug discovery working, and pursued it with folks like, incredibly inspiring folks like Jeff Reed and others at Regeneron. This is an example of how it can really work. They had a very specific idea of how they were going to use it, just like outlined in that New England Journal paper, as a matter of fact, for the world to see. And it's really exciting to see it work in practice. I mean, I think they're at something around 100,000 whole exome sequences, and going for 250. I think George said 500 maybe. Only a matter of time before they decide to go for 1 million. And given the efficiency and focus, they are likely to get there, very, very rapidly. I think it's important to have a bias to action versus sort of endless recursive contemplation and top-down strategizing. I think you can go crazy with having endless meetings and meetings and meetings of this top-down view, because the world is going to change. There are all these things you're going to discover once you start to develop these. And so I think you have to have the critical guardrails in place of security and compliance, which is obviously critical to our platform, in place, but then recognize and have the ability to adjust versus, sort of stick to some plan that you develop before you really knew as much as you need to know. Perfect is being the enemy of the good. And again, it's incredibly powerful to bring data, people, and tools together. and that when given the opportunity to collaborate, people really like to do it. Okay, last couple of minutes here. Really one of the most important topics is that as important as technology is in achieving the promise of precision medicine, realization is all about impassioned champions. Innovation is driven by champions. I repeat that. Innovation is driven by champions. This is true in drug development. There's a great Flowers and Mellman paper where it said that every drug they could identify made it, like at one point had some reason, very good reason to plausibly kill the development, but it made it through because of a clinical champion, someone who championed the program. I was really inspired by a talk from the late Judah Folkman that he gave where he said innovation is driven by inquisitive physicians, inquisitive researchers, and now I'm sure he would add inquisitive data scientists. I would say that when I describe what our platform does as an example, it is to empower, it's not to solve people's problems, it's to empower those inquisitive physicians, researchers, and data scientists to unleash their imaginations and passions and to let loose on the data and to really make progress. And of course, this all comes back to the famous Margaret Mead, which I really love. I never doubt that a small group of thoughtful, committed citizens can change the world. It's the only thing that ever has. And sort of my final slide here, which is just an example of all the different precision medicine champions. I feel like we've, this is just sort of representative examples. There are many others I could have picked here. On the research, the folks on the left who were really incredibly, Charpentier and Dudna, who were incredibly important in the elucidation of CRISPR. Patient champions like Matt Might and his family, as we discussed. Data champions like Regina Holliday and if any of you, I'm sure there are Kims, you probably have seen her jackets in the walking gallery. Clinical champions like Alice Shaw at Mass General, a clinical oncologist whose deep knowledge of science and passion for patients really enabled her to deliver high quality sort of precision medicine inspired care. Dr. Taha Kasut, unbelievable inspirational figure in government at the FDA. Collaboration champions such as Stephen Friend and John Wilbanks and their incredibly important role at Sage Bionetworks. There's so much that they have done, not only in terms of allowing people to collaborate and work together, but also in terms of, I think the work that they've done, some in collaboration with Apple, but particularly in terms of patient consent and in really making it possible to go from the fact that patients deserve to see the data, their own data, to making it actually happen. And I really can't speak highly enough of the of some of the efforts of this group. Although if you want to hear more about John Wilbanks, you can listen to the Tectonics podcast because we interviewed him on it last year. And then finally, translational champions, many examples. I'm especially fond of the work and the thinking of Susan Desmond-Hellmann. I might have also added a Atul Butte here, folks who really appreciate the challenges of translation and the importance of having the very best people work together on the challenges of bringing together leaders from academia and industry. And instead of focusing on difference and saying, oh, you're in academia, you're in industry, you're in doing this, realize that these are unbelievably difficult problems that we're facing. In order to cure disease, in order to make impacts against complex, challenging, difficult problems, the only way on the planet to solve this is going to be by getting the very best people to work together and toward solutions. So hopefully you'll be one of the, if you're listening, you will be one of the precision medicine champions as well. I'm really grateful for your time, and let me see what I see in the way of questions. Are there other questions that come up now? There's sort of a more detailed question that maybe I would answer offline. Any other questions that I can answer, or Judy, should I wrap up? What do you think? Happy to.
Thank you, Dr. Shaywitz, for that informative presentation. It is time for Q&A. So if you have a question you'd like to ask Dr. Shaywitz, please do so now. Just click on the green Q&A button at the lower left of the presentation window, type your question into the box that appears on your screen, and click on the send button. And a question that has come in that that you feel is too technical for the general audience, Dr. Shaywitz will perhaps you could answer that on a one-on-one basis. As we're almost out of time, I'm thinking that, again, Dr. Shaywitz would like to thank you for your presentation and wonder just if you have any final comments you'd like to share with us.
That's been made. I guess I really am a strong believer in grounded optimism. I think that people given half a chance, the extent that we can, through realistic, that we are able to empower patients, that we're able to share data. A lot of these things sort of sound like feel-good buzzwords, but I think, when you're face-to-face with a patient who has a condition, is really trying to, the way that it's so hard, that for patients with, let's say, I think it's particularly poignant in oncology, where it seems so hard not to have nominal data sharing relationships, but the amount of information that gets left on the table from even an individual clinical encounter to like if someone comes into clinic and you're not able to, you don't necessarily know what to do, the first time you see them, it's already unfortunate. But then if someone comes into a different, to the physician who's across the hall from you, and they've not been able to learn from what your experience is with your first patient, that really starts becoming inexcusable. And as that sort of multiplies, there's so much opportunity, there's so much data that are left on the table and opportunities for learning. And I think we really owe it to our patients to really capture and to integrate as much data as we can, and to really learn what we can, and to bring it together with empathy and understanding, and really try to improve the care that we have.
So we do have another question for you, possibly a couple more general questions. How is the participation of the regulatory and control in a team?
Where to share data from the web page or especially? I'm not sure. How is the participation of the regulatory and control in a team? To be honest with you, I don't understand the question, but maybe if whoever wrote it is able to email it to me. So the question is, how is the participation of the regulatory and control in the team? I don't understand the question. So, but if someone, maybe she's trying to be quick, but if she writes in more detail, or I'll be able to, happy to offer a more detailed response.
Yes, the remaining questions, that would be great if you would respond via email. We will now be opening the DNA Nexus website on your screen. This will open in another browser or tab on your computer. Okay. This is an educational webinar and thus offers free continuing education credits. After the webinar is over, and to get your credits, click on the button located in the bottom left-hand corner of your web page. Before I go, I want to let everyone know that today's webcast will be available for on-demand viewing through November 12th, 2016. You'll receive an email from LabRoots letting you know when this webcast will be available for replay. Please share that announcement with your colleagues who may have missed today's live event. That's all for now. Thank you for joining us. We hope to see you again soon. Goodbye.